Hey, what is up guys? For this question, I'm going to be solving Leetcode 133, clone a graph. And the question here asks us to do a deep copy of a connected and undirected graph. So there's two questions that pop up initially. First of all, what is a deep copy and what's a connected undirected graph? So an example of a connected undirected graph would be something that looks like this. You have nodes and edges that are connected, but there is no direction in any of the edges that come out of the nodes. And a deep copy would be, we're given a node like this, for example, 1. A deep copy would be not just returning a copy of 1, but you return a copy of 1 and all of its edges. So you make a copy of whatever it's connected to. So 2, so you make another copy of 2 and another copy of 4. So a copy of the node itself and its neighbors. So you need to copy all of the elements in the object. So there are a couple ways to do this. The approach that I'm going to take is pretty simple, and I broke it down into 2 steps, but I think you can combine it all into 1 step. So initially I'm going to pretty much just create a copy of the graph and put it in a dictionary format. So if I were to use this example to follow the one that I just drew here, then I want to put this in a dictionary format. And what that would look like is we're going to have the key being the node itself, the node.value, and the value of the dictionary would be the neighbors. Also their value. So for example, in here, the dictionary for this graph is going to look like this. We have 1, and I'm just going to write the first one and speed up the remaining. So we have 1 that connects to 2 and 4. Once we have this graph in the dictionary form, all we need to do is iterate through it and create the new graph. So the way we can do this is we can take advantage of a new dictionary. And for this, we're going to have a key of its old value and its value being the new node that we create. So for example, once we iterate the key value in our old dictionary, we can check in this new dictionary if we have this key as a value. If we don't, we create a new entry in the new graph. If the key doesn't exist. So let me go through an example. If we start with 1, right now our new graph, let me just put it at the bottom here. Our new graph is going to be a dictionary that just has 1. And we're going to point that to the new node. So we're going to create a node like so, with 1 being its value based on the definition here of the class of a node. And we're going to point that as the value here. And next we're going to iterate all the neighbors and either create or simply check it if it's in the dictionary and update the neighbors for the node that we created above here. So for example, in this example, when we go through 2 and 4, we don't have 2 and 4 in the new graph. So what we're going to do is we're going to create 2. We're going to add a pointer to the new node here. And we're also going to create 4. We're going to add a pointer to the newly created node here. And once that's done, we're going to append those nodes as neighbors to this node 1, which we created above. So now in that first loop, when we process this, we're going to have 1 as a newly created node, and its neighbors are going to be 2 and 4. We don't have this stored in the dictionary, but all we need really is the reference to the new node 1. So this new node 1 is going to have its neighbors being 2 and 4. And now once it goes through another loop, it's going to go through 2. So now we check in the new dictionary, do we have an entry for 2? And we already have it right here. So we don't need to create a new node. We can just reference the dictionary and get the reference to this node that we created. And now we go through the array here, 1 and 3. And we can check the dictionary again. Do we have 1 in the dictionary? Yes, we do. So we can do the node for 2. We can append its neighbor as this node here in the dictionary. And that's how we can get the reference for it. So once we keep repeating that on and on, we're going to end up with the very last entry of 3. And now all we need to return to finish this question, once we process all the elements in the dictionary, we're going to build our new graph by just using this intermediary new graph, new dictionary, as a helper method to get a reference of all the other nodes. It might seem a bit tricky, but I think going through the code is going to solidify this. So let me just jump right into that. So as a starter, we can just have a basic check. If we don't have a node, we can return an empty. And now we can store this old graph dictionary. This is going to hold the state of our old graph before we do the copies. And we're going to need a method to populate that. We'll just call it DFS, which is going to pass a node, a dictionary, and a scene array. So we don't go through another loop of a node that we already seen. So I'm just going to call this DFS function with a node that's passed into this clone graph method and the old graph. So to populate that, and scene is going to be empty initially. So what we can do is, if the node.value is in scene, we can just return from here. Otherwise, we can add it to the scene method, scene dictionary, and go through each neighbor. And we can, again, check if this is seen. Maybe actually we don't need to check because we're going to call it above here. But now what we can do is we can append this dictionary, which is going to be the old graph, the node.value, and its neighbors is going to be an empty list initially. And now we can do append neighbor.value. And I'm going to print this dictionary just so we can see clearly to what this does. And now we just need to call DFS on the neighbor, pass in the dictionary that we're using, and the scene dictionary. So right now we have 2, 4, 1, 3. So if I print this old graph, it should show that. And I can return a none for now temporarily. So we have 1 is connected to 2 and 4. Oh, the format of this is 1 indexed. So this is index 1, this is index 2, this is index 3, this is index 4. So in index 1, we have a node of value 1 connected to 2 and 4. In the second index, we have a node of value 2 connected to 1 and 3, and so on. This old graph dictionary has a representation of what this current graph looks like. And now all we need to do is iterate it. The key value in old graph.items should give us what we want. And we can use this as a temporary dictionary to store a reference. And all we need to do is return new graph in the end for 1, because the question here says the given node will always be the first one with values equal to 1. So we just need to return the copy of that node. So this is going to be the value of 1. is going to give us the reference to the copy of the node that we created. So now we can check if the key is not in new graph, then we can create a new node with this key, and we can fetch this now, and we can go through each neighbor, and we can pretty much do the same thing. We just need to check if the neighbor is not in the new graph, then we're going to create a new node based on this value, and we're going to have a reference to the old value, and the value is pointing to this new copy that we created. And now we can just do node.append and neighbor.append would be this new graph neighboring value, which is going to give us the reference. So once that keeps running, I think that should solve that question. Key error in this. Oh, this should be new graph. We just created a new reference here in a new entry in the dictionary, and that should solve it. So I think we can summarize this method, or we can do it at the same time when we're iterating the graph, but it might be just slightly a bit more complicated, and I don't think it offers us any faster time, I should say. So that's why I decided to do it in two split ways. Just first build a copy of what the graph looks like, and then using that, create new copies for each entry in the graph. So I think the confusing part is actually coming up with the depth first search to populate the graph. That's really the tough part, but once you have a representation of what the graph looks like, all you need to do is go through that representation and just pretty much make a copy of all the nodes in that graph. So just circling back to here, we first had a depth first search approach to come up with this format, and once we had it, all we needed to do is iterate it and create this format so that we're able to reference all the deep copies that we made, so that when we're at, for example, when we're in this stage, when we're looking at node number 3 in the old graph, we go through the neighbors. We want to see if we should create a new copy of 2, or we've already done that before, and we can reference it from the new graph dictionary. So yeah, I hope that made sense. Might seem a bit confusing, but just going slowly through the code and understanding what it does, it uncovers that this problem is a bit simpler than what you might think. Thanks for watching.